Alright, welcome grade 12 to a few select questions from exercise 6, where we here have p representing an irrational number, and we're going to write everything in terms of p. So if we look at this first one here, we've got the cos of 18 and the cos of 12. So it's not very clear how can we get the cos of 12 to the cos of 18. Well, we really can't, but there's something interesting about 12 degrees plus 18 degrees gives us a special angle of 30 degrees. Which means that I can write 12 degrees as 30 degrees minus 18 degrees. Thus here, let's go. We're going to say, well, this is 30 minus 18. Well, this is our cos compound angle, which is going to be cos 30 degrees times the cos of 18 degrees plus the sine of 30 degrees times the sine of 18 degrees. Alright, well, the cos of 30, that's a special angle, and that we can know is root 3 over 2, and the cos of 18, well, that's our p. The sine of 30 is also a special angle of a half, but you will have already seen that the sine of 18 degrees in your diagram is 1 minus p squared. So if we go and look at this, well, that's pretty much our answer in terms of p. We could write it as a single term, root of 3p, plus the square root of 1 minus p squared, all of that over 2. Okay, the sine of 78. We can do a similar thing to say, well, 78 degrees can be written as 60 degrees plus 18 degrees, and use compound angles there. But there's also another interesting result that we can use our cos of 12, because 12 degrees plus 78 degrees are 90 degrees. So therefore, 78 and 12 are complementary angles, and sine and cosine are complementary functions. So the sine of 78 degrees is actually the same as the cosine of 12 degrees, which means this also is the root 3p plus the root of 1 minus p squared, all of that over 2. You would have got there if you'd also used 60 degrees and 18 degrees, but obviously this here is a little bit faster. Alright, 2 cos squared 9 degrees. Okay, well, we can see that 9 degrees is half of 18 degrees, and this is very close to our compound. 2 cos squared theta minus 1 can be written as the cos of 2 theta, but we're missing this minus 1. So, if we go and add it in, 2 cos squared 9 degrees minus 1, well, that's our double angle, but now we have simply subtracted 1, and this is no longer the same expression. But if we add 1, well, then it is the same expression. And then this part here, well, this is our cos double angle. So this becomes the cos of 18 degrees, and we've got plus 1. Well, the cos of 18 degrees is our p. So we have p plus 1. Alright, sine squared 9 degrees. Now this is, you might think to try and use this identity. But that looks like a lot of work to try and add in not only one, and add in a 1, but also we have to have a negative 2 that we have to add into this whole thing. However, if we realize, well, that my cos, we've just worked out that I know something about cos squared of 9 degrees. From grade 11, we know that sine squared theta can be written as 1 minus cos squared theta. That's your Pythagoras identity. So this here, we could write as 1 minus cos squared of 9 degrees. Now, we don't know what cos squared of 9 degrees but we do know what the cos squared is of 2 cos squared 9 degrees is. So we can bring that in to say, well, this is 1 minus a half of 2 cos squared 9 degrees. That's the same expression, and then this part is p plus 1. So we have 1 minus a half of p plus 1. So we're going to have here 1 take away a half if we think about distributing this in. So we're going to have a half minus a half of p, or 1 minus p over 2. And now if we look how this leads on, well, we know what sine squared 9 degrees is. Now they're asking us for 9 degrees, the sine of 9 degrees. Well, that's just going to be the square root of this expression that we have just found. Okay, let's look at question D, and I'm jumping down here to D6, which is also not immediately obvious what we're going to do with D6. Right, if we look at these 58 and 20 degrees, that doesn't exactly lead us to 12 degrees, but we do see our compound angle for cos, the cos of alpha cos beta. And if this is minus, well, we'd be looking at adding the angle, so this is sine of alpha, sine of beta. So we realize here that we can write this expression as my cos compound angle, which is going to be 58 degrees plus 20 degrees. That gets me to the cos of 78 degrees. Now, 78 degrees, well, if I'm looking at the angle we were given 12 degrees, 78 plus 12, that's 90 degrees. Which means if I take the complementary angle of 12 degrees, well, the complement of cosine is sine. So this is the sine of 12, which is just m. Okay, question F. I'm going to work through all of these ones here because the given information here, cos squared 23 degrees is equal to t, is not conventionally. We're not used to being given the squared function. So let's look at the first one here. We are given the sine squared of 337 degrees. Okay, so our first thought should be to reduce 337 degrees, remembering that a squared function is going to remain positive, but 337 degrees is all the way around here in quadrant 4, and importantly, that leaves me an angle to the x-axis of 23 degrees. So I can reduce this, even though it's in quadrant 4, it's the positive sine squared of 23 degrees. Alright, if I've got sine squared 23 degrees and I want cos squared, we can use our grade 11 identity that sine squared theta can be written as 1 minus cos squared theta. So we can write this as 1 minus cos squared 23 degrees. Well, cos squared 23 degrees is t, so we have 1 minus t. Okay, now we're given the sine of 23 degrees. Now, there's no way to immediately convert the sine 23 back to cos squared of 23 degrees. But let's go and look at what happens in our original diagram. If we have a reference angle of 23 degrees, they tell me that the cos squared of 23 degrees is equal to t. Well, algebraically, that means that cos of 23 degrees must be equal to the square root of t. Now, the square root of t in the ratio of cos means that my adjacent will be the square root of t, and my hypotenuse is still 1. We can therefore go and work out the opposite, and the opposite here is going to be the square root of 1 minus the square root of t squared, which we can just write as the square root of 1 minus t, which is quite nice. So this opposite side is 1 minus t. Well, in that case, the sine of 23 degrees in this triangle is the opposite, which is the 1 minus t over the hypotenuse of 1. So we can leave it like that. Alright, let's go and see now cos of 46 degrees. So we immediately see 46 is the double angle of 23 degrees. And with cos, we've got 3 options, but the most straightforward will be to use the cos squared identity, cos squared 23 degrees minus 1. Well, if our cos squared 23 is t, then we have 2 times t, not t squared, just t, minus 1. Alright. Question 4. The sine of 46 degrees. Okay, sine only has one double angle, so we're going to write this as 2 times the sine of 23 degrees times the cosine of 23 degrees. Now this triangle here, if we look, will become immensely helpful, because the sine of 23, what we've already seen, that's the root of 1 minus t. And the cos of 23, well, that's the adjacent over the hypotenuse, which is just the root of t. Now, if you remember your grade 11 surd laws, we can write this here. We can multiply. That I actually have here 1 times t, which is t, minus t times t, which is t squared. Because we have the same root, we can multiply, which leaves it looking a little bit nicer. Okay. The tan of negative 226 degrees. Alright, now this function is a single function. To negative 226 degrees is all the way here in quadrant 2. And my reference angle from negative 180, this here will be a 46 degree angle. But of course now with this function we are in quadrant 2 and it's not squared. So we are looking at the negative tan of 46 degrees. Now we don't have tan double angles in grade 12, so we're going to write this as the negative sine 46 degrees divided by the cosine of 46 degrees. We've already seen that the sine of 46 degrees is 2 root t minus t squared. Well, we've now got the negative t minus t squared. And the cosine of 46 degrees, well, we've already seen that that one is 2t minus 1. So in our denominator, 2t minus 1. And then there's our answer in terms of t. Alright, the final one, question 6. The sine of 37 degrees. Now again, we have to relate what is going on with 37 degrees and our given angle of 23 degrees. Well, if we add 37 degrees plus 23 degrees, we get 60 degrees, a special angle, which means I can write my 37 degree angle as 60 degrees minus 23 degrees. Thus, we can look at this angle as the sine of 60 degrees, a special angle, minus the given angle of 23 degrees. If we go and expand this using our compound angle, the sine of 60 times the cosine of 23 degrees minus the cosine of 60 times the sine of 23 degrees. Well, the sine of 60, that's the root of 3 over 2, multiplied by the cos of 23, and we've seen that the cos of 23 from our triangle is just the root of t, minus the cosine of 60, which is just a half, multiplied by the sine of 23, which again from our triangle is 1 minus t. We can go and neaten this up and write it as one term. We can write this as the root of 3t minus the root of 1 minus t, and all of that is over 2. Okay, let's have a bit of fun here with h. Alright, although it's got a star, let's take it one step at a time. And the first thing we notice, the given angle is 10 degrees, which I have in this first one here. But these angles are 70 degrees. Well, 10 degrees plus 60 degrees is 70 degrees. So I'm going to rewrite the cosine of 70 as 60 plus 10. And we're going to write the sine of 70 as 60 plus 10, multiplied by the tan of 10 degrees. Alright, let's expand out these compound angles and see what it leaves us with. We have the cosine of 60 times the cosine of 10 minus the sine of 60 times the sine of 10. Then we're going to add and inside brackets, because this expansion of sine is going to be two terms, and we're going to multiply it still by the tan of 10. So we need to keep it in brackets when we expand. This is going to be the sine of 60 times the cosine of 10, but I'm going to keep the plus, and then we have the cosine of 60 times the sine of 10 degrees times the tan of 10 degrees. Okay, let's have a look at what this is leaving us with. cos 60, sine 60, sine 60, cos 60, all of those are special angles which we're going to be able to look at in their ratios. But the cos of 10, well, there's our k. The sine of 10, we can't write. We can't convert sine 10 to cos 10, but we can look at a diagram. And in fact, looking at a diagram is going to help us a lot, because we can even make sense of what the tan of 10 degrees is. So if this is my reference angle, the given information, cos of 10, would be adjacent k over the hypotenuse 1. And by Pythagoras, then, this is going to be 1 minus k squared. Which means, if we look at this, our cos of 10 is k, that's what we had. Our sine of 10 is going to be the root of 1 minus k squared. And our tan of 10 is going to be the opposite, 1 minus k squared, over the adjacent k. So using this information, we can go and do a whole lot of substitution all in one go. Just leaving myself a bit of space here. The cosine of 60, well, that's a half, times the cos of 10, well, that's k. Minus the sine of 60 is the root of 3 over 2, times the sine of 10, well, that's root of 1 minus k squared. Right, plus the sine of 60, well, that's the root of 3 over 2, times the cos of 10, well, that's k, plus the cos of 60, well, that's a half, times the sine of 10, which is 1 minus k squared, the root. And the tan of 10 is 1 minus k squared over k. Well, this is looking better. So if we think about, we're going to go and distribute this into both terms and tidy things up a little bit. Half of k we can write as k over 2 minus, if we go and multiply here, we're going to have the root of 3 times the root of 1 minus k squared, which you could go and multiply 3 and k squared, all of that over 2. Plus, our first term here is going to have the root of 3 times k times the root of 1 minus k squared. All of that's going to be over, in the denominator, 2 times k, 2k. Plus, in this first one here, well, we see we're going to have 1 times the root of 1 minus k squared times the root of 1 minus k squared. So we're multiplying that root by itself, well, that's just going to be 1 minus k squared. And in our denominator, 2 times 1 times k, 2k. Sorry, not k squared, let's leave it as k. Alright, let's look at our denominator here. We've got 2k and 2k there, so these two terms just need to be multiplied by k. And then we're going to have the same denominator. And in doing that, we notice something interesting happens with these two terms here in the middle. That in fact they're the same term. And if we subtract it and then we add, well, those are going to undo each other. So if we look at what we've got left here, we have got a k squared over a 2k plus 1 minus k squared over 2k. Well, if we add k squared and negative k squared, we're left with 0k squared, so we've got 1 over 2k, which is the answer. Alright, let's tackle the last one, question 2. Okay, right, we notice here that we've got tan of 5 degrees. We don't have tan double angles in grade 12, but we can see with 5 degrees that we're going to have to do something with double angles. So let's go and think about, well, we've learned in grade 11 that 1 over tan theta is the inverse of, or the reciprocal of tan, which we could therefore write as cos of theta over sine of theta. So this first term would make sense to write this as the cos of 5 degrees over the sine of 5 degrees minus, and then here we're going to write this one as the sine of 5 degrees over the cos of 5 degrees. What do we see now is that we're subtracting fractions. So if we take a LCD of cos 5 degrees sine 5 degrees, in this first term, we're going to multiply by cos over cos. So we're going to get cos squared 5 degrees. And the second term, we're going to multiply by sine over sine. So in which case we get sine squared 5 degrees. In our denominator, we've got our LCD, cos 5 degrees times sine 5 degrees. Well, in our numerator, we can see that's our cos double angle. So this becomes the cos of 10 degrees. But in our denominator, we don't quite have our sine double angle, but we're close. Because if we take a half times 2 sine 5 cos 5 degrees, so now we realize that our denominator can also be written as a half of the sine of 10 degrees. Well, if we look at what we were given here, we do know what these values are. So the cos of 10 degrees, we have seen, well, that's our k. The sine of 10 degrees, well, that's the root of 1 minus k squared. We can write this, if we're dividing by a half, we could write this as 2k over the root of 1 minus k squared. Okay, I hope that was helpful. Best of luck.